Hello everyone, this is Professor Kuehn. We have been discussing the cohesion of substances. We've been looking at Chapter 2 of A Student's Guide to the Great Physics texts, where Salviati, Segredo, and Simplicio are debating what it is that holds things together. You might remember in the last lecture, what Galileo suggested that we do is we try to measure the strength with which nature abhors a vacuum, or rather, how much force it takes before nature in fact allows a vacuum to form. And the technique that he used was to have a column of water and apply a force to it in order to break that column of water, that is to create a vacuum inside of it. And they found that it takes a weight equivalent to about a 30-foot column of water. So the question that next arises is, can this abhorrence of a vacuum that nature seems to express account for the internal cohesion of other substances, for instance, copper wire? So let me cut away from my webcam here and go to my sketchbook. So this is the apparatus that Galileo used to try to measure the strength with which nature abhors a vacuum. And the next topic is discussed on the following page or two. And here's the question. So the question that is now being asked is, can nature's abhorrence of a vacuum account for the cohesion of, let's say, a copper wire? That is a question that we're asking. And the answer, let me just jump to the answer right away, is that the copper exhibits this internal cohesion that cannot be completely attributed to nature's abhorrence of a vacuum. So I'll just write no. It can't account. It seems like copper is more cohesive, or it's harder to break than one would anticipate if you were strictly to attribute their cohesion to nature's abhorrence of a vacuum. So how does he demonstrate this? So he imagines doing this. Let's suppose we take a ceiling. Here's a ceiling. And you take a length of copper wire. So let me make the copper wire, well, let's make it this color. So here's a copper wire. And from the copper wire, you hang a weight. Okay? And let's suppose that this copper wire has a length of, let's use the numbers that Galileo uses, 1 cubit. That's 1 cubit, which is about 18 inches. The weight, so 1 cubit of copper wire has a weight. And let's suppose that it's a narrow gauge copper wire, and we make it just narrow enough so that 1 cubit of copper wire weighs 1/8 of an ounce. Okay, so that's the weight of this wire of copper. And when you do this, you will find that it will, if you hang a 50-pound weight from this copper wire, it will just break it. If you put less than 50 pounds, the copper wire will not break, but if you put more than 50 pounds or exactly 50 pounds, it will just break this wire. Okay? So this is step 1. Okay, step 2. Now, let's suppose that you take this weight off, and instead of the weight, you just put a bunch more copper wire hanging from it. After all, it doesn't matter whether the weight is a piece of iron or just more copper. So here's the ceiling, here's the copper wire, and you hang enough copper wire. I'm going to put some breaks right there, a really long copper wire. So at the top of it here, we still have this 1 cubit right here, and then you hang a whole bunch more copper wire down here. And we find that if you hang enough copper wire down here, then this copper wire will break. How much wire is required to do that? Well, 4,800 cubits. If you hang 4,800 cubits of copper wire, that is equivalent to 50 pounds of copper wire, and that will break it. How do we know this? Well, Galileo goes through the calculations. He says, since 50 pounds is equal to 600 ounces, I remember being a little bit perplexed by this when Galileo first mentioned this, but he's using troy ounces. So troy ounces, 12 ounces, 12 troy ounces aren't a pound, so 50 pounds will weigh 60 troy ounces. And 50 pounds will be equal to 4,800 times 1/8 of an ounce. Remember that 1 cubit weighed 1/8 of an ounce, and so if you have 4,800, each one weighing 1/8 of an ounce, you'll find that that's 600 ounces, and that is just enough to weigh 50 pounds and to break this copper wire. That's at the top. Now notice that this is the case whether you have a single wire or if you hang 2 wires side by side. 2 wires side by side, each one you'd need to hang 4,800 cubits of wire from beneath it in order to break it, or 3 wires or 5 wires. Or in fact, if you took all these wires and bound them together into a single very thick copper wire, it would still break with 4,800 cubits of wire hanging beneath it. So we could use one wire, or several, or one thick wire, or one very thick wire. And in any case, it will break if there are 4,800 cubits of the same thickness of wire hanging beneath it. So it's in other words, it's independent of the diameter of the wire. Now the question is, why can it be extended to this length before it breaks? So you might imagine you've got this wire hanging from the ceiling. How much wire can you hang before it breaks under its own weight, 4,800 cubits? Why is it this particular weight and not some, why is it this particular length and not some other length? Well, one of the ideas that Galileo comes up with is that, well, maybe it's got this, maybe the nature's abhorrence of a vacuum is able to account for this. Okay, well, we can test whether that's in fact the case. So let me make this a little bit larger so we have a little more real estate to work on this problem. Okay, so the question I want to ask now is, can nature's abhorrence of a vacuum account for this? I guess I don't need to rewrite that because that's the question I have at the top of the other side. So what would we expect if nature's abhorrence of a vacuum is able to account for this cohesion of wire? Well, we know, this will be point 4, that copper is 9 times as dense as water. So it has a specific gravity of 9. It's 9 times denser than water. So we know that a column of water, and this is from the last lecture, we know that a column of water can be extended to a height of 18 cubits before it breaks under its own weight. So we would expect, since copper is 9 times denser, since water breaks under its own weight at a height of 18 cubits, that's when a vacuum forms. So that's kind of the strength with which nature abhors a vacuum. And the density of copper, or the specific gravity of copper, is 9. Then we should only be able to extend this copper wire by 18 cubits divided by 9, or 2 cubits. In other words, if nature's abhorrence of a vacuum can account for this, then as soon as we have a 2-cubit wire hanging from this, then it should break under its own weight. But copper can be extended to 4,801 cubits. That's this 4,800 plus this 1 before breaking. And only 2 cubits of this can really be accounted for by nature's abhorrence of a vacuum. So the extra 4,799 cubits have to be attributed to something else besides nature abhorrence of a vacuum. So point 7 is that nature's abhorrence of a vacuum only accounts for the cohesion amounting to 2 cubits. 2 cubits worth of cohesive force. The other 4,799 cubits worth, I guess, weight of cohesion must be attributed to something else. This is how Galileo reasons. What else can this be attributed to? Well, this brings us about up to page 19, and the first thing that they consider is maybe there's some kind of internal gluey substance or bonding substance that supplements nature's abhorrence of a vacuum in holding this copper wire together. This is not what ends up being the thing that Galileo pursues, and we'll see how he addresses this problem.